So we're going to talk about kind of our concept of what we view as kind of a containerized container platform. And I'll explain what that means since it might seem a little bit meta. So I'm Ken Robertson. I'm from Apcera, lead architect. And Apcera has a platform, or well, we call it the Apcera platform. And it's a container platform that's largely focused on security and policy. But I'm not really here today to talk about the Apcera platform. Instead, I mainly mention that to actually rewind to the beginning of Apcera back in 2012. Apcera set out at the time, our CEO, Derek Collison, was the original architect of Cloud Foundry. And we were looking at kind of going beyond what Cloud Foundry and PaaS systems were then. But at 2012, we chose to adopt the Go language. Go 1.0 had just come out during that time. But the Go landscape back in 2012 was kind of barren. There wasn't really anything in terms of libraries to build off of, best practices to help you get going. So when we started out, we really had to kind of build everything from scratch. Docker didn't even come out till 2013, which was kind of one of the first large-scale Go applications that got a lot of attention. So we kind of had to build everything from CLI tooling to also our own container instrumentation. We chose to kind of go low level for implementing the containers because as a security and policy focused system, we wanted to be involved both on the high end of definition of security and what you can do with the system, but also the low end in terms of making sure those are all instrumented, audited, and enforced, and everything. But over the course of 4 years, we kind of built this system that ended up looking a little bit like this, where in our system, what manages a container is called an instance manager. And we started out very simple, kind of, a container is rather simple, instrument this, that. But over time, it grew to where we had a cgroups container manager, which had an interface because we also had a simple container concept for running unit tests on OS X or something. And then cgroups container contained all of the logic for managing the life cycle of an individual application in its container. And it called out to several libraries like netfilter, cgroups, mounter. But we ended up with this really kind of bloated piece. And so it ended up kind of like this monolith, which kind of parallels some people's view of things like Docker, where it's very large in terms of all that it manages and hard to get newer things in. As things grew in cgroups container for network instrumentation, it just kind of made the monolith even bigger. And it became a difficult model to maintain. Even one thing from this, actually, you can see like all these different things have their own paths back to our control plane, simply because as things grew, there need to be more communication paths where things would either need to call out to the control plane or receive messages from it. And it became very difficult in terms of testing to mock something like this out, to give it a well-defined API, to ensure you can have alternative implementations and such. So the instance manager, in our view, kind of started out simple, but became this massive monolith. Over time, we got to a place where we had 8 states for a container. So it would go setup, starting, first running, updating, stopping, teardown. And we had 53 functions that went across all of these states. So we tried to kind of decompose it into these scoped functions, but it just ended up becoming this really ugly kind of state machine that was no longer fulfilling the original ideal of keep it simple. We called out to several libraries for things like Mounter, which handled remote mounts and cgroups and such. But most of the integration logic for that was still centrally located. So those would do individual functions for managing network or creating a mount, but then ensuring everything is still wired up was entangled in that massive monolith. Additionally, the deployment system that we had was much more heavyweight. The host machines that would be running the containers were based on Ubuntu, to where they'd have that 700-800 megs of overhead. We were using CAPS, or Chef, Ansible, Puppet, Salt. We actually were using Chef primarily for managing the deployment and updating, packaging our system as devs, and then that host also having all kinds of operational tooling. Generally trying to keep them light, but there'd be sometimes we'd have part of GDB installed to take a core dump of something, or other things where developers would be logging in, or operations would be logging in to capture log files and things like that. So each of the machines kind of ended up very heavy. And we wanted to kind of get to something simpler. Over time, as we were building a product and not so much of a service, kind of productizing that type of deployment is very tricky. It'll go out to customers, and then some of them are managing it themselves rather than us. But with this kind of cycle, deploys end up kind of being non-atomic. Since we were distributing Debian packages and updating it over time, each host has its own kind of life cycle. Whether it had version A to B to C, or another one had B to C, or another one is new in C, that kind of the different versions a host had meant over time there were subtle variances in terms of what had been previously on that host or not. And then just the kind of operational aspect to it. An operations login captures a log file or a core dump and then forgets to remove it when they log out or something like that. Would lead to variabilities in host or disk space. If there was a database outage because the root volume filled up because they were doing backups when they were doing migrations. So about a year ago, we started a project to kind of go back and look at kind of a platform v2 for our own system. And that involved rethinking kind of our container management, making it so that the container management was not buried inside of this instance manager process, but instead was something that was separated on its own, kept very simple, and instead very focused on extending outwards to where our own system can be hosted by it, and it can use itself to kind of launch additional containers. So Kurma was a project that we came up with. Kurma is the name of a Hindu god for the world turtle concept, which is basically the world rests on the back of a turtle, and it kind of comes from the saying of turtles all the way down or containers all the way down. With Kurma, we wanted to go back and look at how could we kind of minimize the host dependencies. So that way we don't need this large operating system, we don't need that operating system's tooling for packaging, we don't need all this other tooling for distributing packages and setting it up. Go back and keep everything very minimalized, focused on everything as a container. So in that way, even system services we'd need could be instrumented as containers rather than other things installed on the host that would have to be installed by something. And we wanted very simple notions that could be easily extended and to have simple defined APIs so that we don't get back into this place where there's multiple paths back to a control plane that we can't maintain a good contract with or track version changes over time. We wanted something just very simple that allowed us to iterate and extend where needed. So Kurma, as it is currently today, at least in the master branch, it's written in Go and C. We use C for the low-level container instrumentation. We've implemented against the app container spec. This came out late 2014 as kind of a more standardized definition of container image, a running instrumentation or running environment for it, as opposed to with Docker, it's kind of the standard derived from a product. This is more of a standard that products can be based off of. And we were using Apcera's own container instrumentation. So kind of this section of code that we ripped out of our old instance manager to be standing on its own. Coming soon, we're actually changing it to be libcontainer based. A lot of this is, while we had our existing container instrumentation and been using it for over 3 years, it's very slim and minimalized, but libcontainers come out and been out for almost 2 years now. Very matured, more eyes on it, and also has all kinds of integrations that we hadn't previously needed in our own system around SE Linux or AppArmor, things like that. So I think this kind of moving to libcontainer allows us to gain some momentum in things that don't differentiate. Adding SE Linux or whatnot is kind of a base requirement for something to be cross-platform rather than something that would make it actually differentiating. And then we have 2 ways of kind of bundling and delivering Kurma. Kurma D, which is just where it's a daemon that can be deployed to an existing host, download, run it, immediately get benefit. And we focus on the contract really only being about the host kernel and libc. In the kernel of the aspect, if you want user namespaces, you have to be on this version and have it enabled. And libc, primarily because there's some issues with Go statically compiling against libc. And libc is pretty standard on any system with a well-defined contract. As well as this kind of Kurma OS minimalist distribution. One of the things we looked at with only depending really on the kernel and libc is the things you get from a host operating system are almost nothing, to where you could have just a minimalist distribution that boots up, has those provided. And in other host services you might need, like syslog or udev or things like, or NTP, could just be run as containers as well. So this is a little bit more along the lines of like a Rancher OS model. But this focuses as the services as containers, or a list of initial containers to run on boot. We have it bundled using AB partition model. So this is kind of how a lot of routers or networking equipment, or even how CoreOS works, where it'll have two partitions, it'll boot up on one, you can deploy an update to it, it'll apply it to the B partition, and then quickly restart on B, and if that fails, it can fall back to what it was on. So this allows kind of easy deployment and failback modeling. And you can still get a container or a console, but this is where the console is just running as a container, kind of a initial privileged container that has access to the host TTY. But in terms of keeping the model simple, we wanted to kind of boil it down to just kind of a simple process model. So in this way, we kind of have just this simple model for Kurma D, a stager, and in this case, a pod. Whenever I refer to a pod, it will always be in the context of a Kubernetes style pod. A stager is intended as kind of a first run process that is responsible for instrumenting a pod. Kurma D will launch the stager and pass it the definition for the pod. Say, hey, I would like you to instrument these workloads. And then it goes off to instrument the individual applications that are specified. It'll also launch in a init process as well in the container. That way, kind of, no container really takes priority over one another for getting PID 1. And it also ensures that the container can, or the overall pod, can maintain an individual app failure. So it can either go in, clean out that application, restore it to a fresh state, and relaunch it. Or stagers could also choose to just completely tear down on an individual app failure. One other thing with the stager is we implemented it in a fashion that allows Kurma D to be updated and restarted outside of it. It's launched as a child and disowned so that its lifetime is independent. And Kurma D can be upgraded. And when it comes back up, it can reestablish a connection with it and check if a version incompatibility for the API is present. And no, it'll have to tear it down, or it's still a version that's compatible and can keep on running with it. And then the individual user processes are just based on whatever was in the pod manifest, as far as if it wants to run a web application and Redis right alongside it or something like that. So stager, again, is responsible for instrumenting the pod. It's based off a signed and trusted ACI image, or app container image. So in this way, stagers can be implemented independently of Kurma. Instrumenting a new one does not require core changes in Kurma. They can be distributed, versioned, and updated independently. And a stager allows pluggable instrumentation of the pods in the containers. By default, it could be one that focuses on a pod model and containerization, but this could easily be one that says, hey, I actually want to launch VMs for the applications rather than containers. Or it can be one that doesn't want to focus on the pod model where namespaces are shared between them, but rather I'd like to deploy the applications fully separated. And each stager gets its own mount and network namespace. Just in this way, any mount operations it does doesn't propagate to the host. And the networking interfaces that end up on the stager are intended to be transferred down to the individual applications. The way a stager works is with the simplest kind of API available. It's just an executable. Rather than focusing on HTTP or other types of APIs, saying I'm going to execute something is the simplest contract. It can pass it command line arguments. It has standard in, out, and error for messaging. and it reuses that concept to where the stager image can have an exec setting or what to run on start, and it expects that that is the primary instrumenter for the stager. It can pass in configuration along standard in just as JSON, and it expects either success results over standard out, errors over standard error, and exit codes as kind of a success or failure. Actually, with the initial process, it expects it to stay alive. Other calls can be implemented just through other expected binaries. It can call a run process to say it'd like to exec something inside of an individual container, or status to get back just a JSON message, or logs to access log files from an individual application. But with that, it kind of gets into a reusable unit. If you look at kind of the stager and the applications it sets up in instruments for KermaD, it's a flexible notation that can be reused for other types of instrumentation. So extensibility is really just about running more processes or more code functionality than what's built into the base system. So the way Kurma does extensibility for something like interfacing on a networking layer is actually with a specialized pod, where it'll launch a stager and give it a manifest for a networking pod. And this networking pod can be running an application that instruments CNI for setting up container networking, or OVS, or something else. In this way, Kurma on start can be given a list of container images to run for networking, and it'll instrument all of them running within a single pod. And this is a special privileged pod that will have access to the host PID namespace so that it can be responsible for setting up networking on other containers. So the networking API is, again, just ACI image focused. In the Kurma base configuration, it's given a list of container images to pull down, and a JSON configuration it'll pass directly to them, so that way they can define their own configuration. And it'll execute individual commands on container setup. So it can call an expected add binary to set up networking for a new container, or a delete to tear it down. So in this case, it'll pass the namespace, base name for the container, and what its interface is. And it'll expect it to run, set up the networking, exit 0 on success, or non-0 on failure. And this is kind of a basic, just example configuration. The default networking model we've adopted is CNI. So this is actually just the CNI bridge configuration, but where the top 4 parameters are specific to Kurma. We use that to specify the image to pull down, a name to make sure there's no crossover, and a little template format for defining what the interface is. So that way it'll use that template to determine if it should tell the container or the networking container to use ETH0 or ETH1. But otherwise, this gets passed directly onto CNI's bridge module. So it's kind of an extensible trickle-down type API where we can call to the stager to say run a process in the CNI container, and then in the CNI container we'll say add and give it the parameter specific to it. The standard in, standard out will all trickle down to it, so we're able to pass it its JSON configuration and getting the response message back from it. But that kind of gets to where the simple process model can be used for extensibility through reuse of it. So right now we use it for networking plugins, and this base process model is still carried through for the management of that individual user pod. But it could be used in the future for something like storage plugins, where the same type of API model could be used for a storage module that either does something like remote mounts with Ceph, NFS, et cetera, or doing localized storage management through like a ZFS, LVM, or so forth. Kurma itself doesn't really focus on having an external API. One of the things we wanted to focus on was how do we, as a security-focused platform, ensure that our base container instrumentation is still secure. One of the concepts we had was that by default, Kurma would not have any remote API. Instead, it could be told a set of containers to launch on boot, and it'll have a socket-based API, and those initial containers can specify through privileges to say, I'd like access to the host API. So it essentially does a volume mount to where the socket can get loaded into an individual container, and then a container can choose to implement a remote API. So in that way, it can overlay its own semantics on how you join into a cluster, whether it's connecting to, whether this is a kubelet that connects to the API server over HTTP, or it might be your own process that connects to NATS or RabbitMQ or some other type of control plane. In this way, this implements logic for trust in terms of when a workload comes into it, how heavily does it trust it? Should it allow privileged containers to be launched? Maybe it's launching itself to where it needs to run other privileged containers, but when it gets to running an untrusted user workload, it's able to enforce those semantics on it of not allowing it to go beyond certain limits. So in this way, one of the base things we have that's distributed with it by default now is a remote proxy API. So this is just to kind of show an example of how an API can be extended beyond it, where we have Kurma's API, just a JSON RPC that goes from the Unix socket to HTTP and allows remote connectivity. But it's able to do some things like not allow privileged containers to come into a system, only standard unprivileged ones. So this can kind of serve as just a base demonstration of how it can be extended beyond itself, but with enforcing those rulings upon it. And Kubernetes and Kurma is one thing that we're working on as well. We're in the process of adding Kurma support to the kubelet and looking to upstream it in Q2, probably starting to show up in around 1.3 release. Why? A lot of it is focused around Kurma usage outside of Apcera. We open source Kurma, and it's kind of pointless to open source something if its repos are public, but all usage of it is internalized in proprietary stuff. But also, open sourcing it and adding community use cases and getting more attention on it also can help flesh it out for your own usage. There's concepts in Kubernetes that were needed some interfaces to be defined in Kurma, and actually led to cleaner implementations by having to fulfill different types of use cases. So pods is one thing we don't have in Apcera's platform, but adding pod concepts to Kurma actually made it more flexible to where some of the instrumentation we did could be done more cleanly by using the stager model. Or implementing networking with CNI actually got it to where some of the networking instrumentation we already have could be cleaned up if we ported them over to just be CNI plugins. The kubelet in Kubernetes already has an existing runtime interface which defines everything that should be implemented on an individual container runtime engine. But the kubelet is a little bit of a leaky abstraction where there are some things that are done outside of that interface, oftentimes that are kind of focused on Dockerisms, or probably more from early on when Docker was the only implementation. And testing, as we've been finding with Kubernetes, is a little bit mystical. There's different types of tests that some are easy to run locally, some are difficult. Some of the CI integration with the Kubernetes project is more of a black box where the CI suite will run and then post logs rather than actually having a more direct interface to it. And there's a number of documentation gaps for kind of how you might run some of its integration tests locally, where you'll try to run them locally and get some failures, but when you push a PR up, they pass. But otherwise, Kubernetes has excellent GitHub and PR integration where, in some cases, other third parties like Mesosphere will post back test status. They have the submit queue, and they have all kinds of automation around sizing, assigning out PRs, and making sure only one lands at a time. So that way, if there's a failure on master, it's able to kind of pause the queue, take a look at that, rather than kind of piling in 5 things at once and not being sure which one kind of broke master. Dealing with the Kubernetes code base, Godep has been a bit of a pain. Godep is one of those things where occasionally it'll just break. You get the latest version of it and it magically works. But also there's a lot of pains in cases where Kubernetes is a large project integrating with a number of things, and there may be dependency overlaps where we're trying to pull in something that's already present but a different version. So you either need to pull back and make sure you work on an older version or try to upstream a newer version of that. One thing that's also interesting is in Kubernetes, there is a hack directory with a lot of bash scripts in it. There's no documentation on what those scripts do, but I magically found out that sometimes you might need to run one of the scripts. Just in one experiment with adding a new field onto one of the HTTP APIs, wasn't able to get it to be sent across by kubectl and persisted to etcd, and went into Slack and they said, oh, you got to run this hack update all script. And I was like, well, what does that do? And they're like, just run it. Ran it, magically worked, but didn't know what it did, or there was no documentation on some of these. And it's one of those things that would be nice to clean up. But just the presence of something named hack is a little interesting. There's also been some interesting interface movement. We're working on adding the Kurma support to the kubelet in 1.1, and took a look at adding it to master or 1.2. At the time is around December. And the runtime had added this convert pod status to API pod status function. Had to add support for it, and then a week or two later went back and it actually removed that function. So there's been some interface movement with, luckily between versions, but some confusing function names and even types where there's two types of pods, there's two types of pod status, kind of depending on whether you're working with something defined from the API or localized to the container instrumentation. So Kubernetes, actually the reuse of the netties I've been seeing a lot. There's Rocket netties, there was Hyper netties in the last talk I was in. Now we're adding another one, Kubernetes. This isn't really kind of a separate distribution, but rather our own internal project name for extending the kubelet to support Kurma. So it's led to a continued maturing of Kurma based on Kubernetes needs. A lot of stuff we had to do was around pod management, pod networking, and image management. Previously, Kurma didn't have anything for image management. It'd expect you to just pass in a location at the time, and it would kind of cache it. It didn't expose kind of which ones it had or when to prune. It would just kind of prune them on that container's teardown. But the runtime abstraction for Kubernetes is nearly complete. We currently have the pod management, image retrieval, and management all implemented. The remaining items that we'll be finishing out over the next quarter, we'll be working on landing Kurma's pod stager branch, which is where we're moving over to libcontainer, and is really needed to kind of finish off that functionality. There's also cAdvisor integration, which will likely be starting as CoreOS is working on adding Rocket to support to cAdvisor. And then also working a lot on integration testing and working on integration testing. And we'd also like to contribute some things upstream in terms of working on addressing some of the leaky abstractions, just as kind of general upstream improvements. Any questions?
So I was wondering if you could talk a bit more about Kurma OS, like what's based on, what unit system it uses, differences with CoreOS or stuff like that.
So Kurma OS is based on Gentoo, and it actually borrows some things from the Chromium OS and from CoreOS, mostly around kind of the GUID partition management for some of the AB deployment. In it boots up, and Kurma itself is PID1, sort of more along the lines of Rancher OS. And it takes care of doing the initial system mounts, mounting disk volume, setting up networking, and then we'll kind of drop into the standard Kurma D. But otherwise, it's not adopting anything like systemd or another more typical host init system. Not specific to the Kurma aspects, mostly because it's not done, and trying to figure out the best way to splice up the PRs so it's not one massive one where it's then going to be difficult to kind of effectively review it. So I'd like to slice it up into individual pieces for like adding a base implementation and then more specific implementation sections. But haven't yet looked at doing that individually with them. We've upstreamed just a few individual changes, mostly around how it does some reporting on the engine version. One thing I'd found initially doing this testing and even testing Rocket locally was if you did describe node, it would always say you were running Docker. Even on CoreOS with it using Rocket, it would say you're using Docker 191. That was just one that was kind of not in the runtime implementation, but rather in the base kubelet that was easy to section off and just upstream.
Yeah, because so the Rocket team, or I'm not sure, I don't think so. They're working in this, fixing the abstraction so it's not Docker specific. Or if you contact them.
Yeah, I've talked with Brandon and Jonathan, and I mean, they and you guys are further ahead with completing the Rocket integration. So we're kind of looking at kind of drafting behind some of those. Especially with some of the C advisor, getting it to be pluggable. That's one thing Brandon had talked about that would be good just in terms of having a third party looking at having to implement something to make sure the API that had to be defined is abstracted enough.
Yeah, that would be great.
So as Apcera, are you going to offer commercial support for Kurma as a product?
That is something we're not at the point of yet. We still kind of consider Kurma to be in the alpha state. We're looking to transition it to a beta within the next couple months. In terms of the business aspects around support, some of that's still being discussed and nothing's really finalized. But one thing to mention as well, we are hiring for the Kurma team, so that way having more people on board, able to increase the momentum, but also being able to field those questions.
So when you get to that point, then I guess you have a choice. Then you have an existing platform and you have Kurma. Are you expecting ultimately there just be one, or
The Apcera platform?
Yeah.
Well, Apcera platform, we want it to be based on using Kurma and Kurma be independent of it as kind of a separate product, but still productized with its own community. We have one other product, which is NATS, pub/sub messaging system, and we're structuring Kurma to be very similar to how we have NATS internally, where it has its own set of engineers that focus completely on it, a community manager, people that set up and manage support contracts and so forth. It'll be following in that model. Thank you.